So in the last Thursday, we talked about, we end with like the value iteration algorithm in a simulator setting. So just recap what is the algorithm is. This is like simulator setting, or we also call this like generative model. So essentially, we have already talking about the value iteration algorithm in the planning task, where we know the transition and the reward. The only difference here is now in the simulator setting, we don't know the transition. So the first step is we need to kind of like estimate the transition. So the way we estimate transition is for all state action horizon pair tuple in all state action on H. We do the following. We kind of like query the simulator. Just remember, in the simulator, we take a state action and a step as an input. And we kind of like query the simulator n times. So we will collect n samples of next states. That is, suppose we collect with S1 prime, S2 prime, until Sn prime. And we will just do a very simple estimation of the transition probability using the empirical frequency of some next state appears. So we will estimate the transition by this. P hat H, S prime, conditional SA is equal to 1 over n, that is total samples we kind of like will query this simulator, and times indicator of how many times I have seen Si prime to be exactly S prime, I from 1 to n. For all S prime in S. And essentially, this is the only thing new in the simulator setting. And the remaining setting will be the same as the value iteration in planning. That is, we just do Bellman optimality equation for H equal to 1. For H from H to 1. Do the following. That is, we will compute Q star hat H SA equal to RH SA and plus P hat BH plus 1 hat star SA. This is like the first step of Bellman optimal equation, where we replace all the Q star V star by the hat version, that is our estimated version. And the only important difference is like because we no longer have access to the transition, so we use our estimate of transition to replace the true one in the Bellman optimal equation. And we will also do the same for the V value. V star H is equal to max A in A, Q hat star SA. Okay. So essentially, we talk about this in the very end of the last lecture. We're saying like the VI algorithm in the simulator setting composed of 2 components. The first component is essentially we use the first for loop to estimate the transition P. Essentially, we get the P hat is our estimate. And the second for loop is just a standard Bellman optimal equation, and we use dynamic programming to compute the optimal value. And finally, we will just output the policy. That is V hat S equal to the, essentially the policy we output is just the greedy policy induced by Q hat star. Okay. So the second phase, essentially, we have an estimated p hat. We know this is not necessarily exactly equal to the p, but we kind of consider it to be close to the true transition in some sense. So essentially, we just do Bellman optimal equation using this p hat, treat it as a p, and also do the output as the same. Like essentially, we just do everything, treated this p hat as an optimal, as a true transition. Okay, so this is the algorithm. So we clearly can think this algorithm kind of makes sense, especially like let's convince ourselves when n go to infinity, we kind of like know by law of large number, this p hat will converge to the true transition p. Okay. In that sense, we essentially in the first step we will learn the accurate transition, and the second step just do Bellman optimal equation. So this is clearly an algorithm or asymptotically correct algorithm when n go to infinity. But since we have learned a lot of tools in the last week or the week before on like concentration inequality, so we'll actually give a much stronger result. We were not only talking that when n go to infinity we get the correct result, but we will also talk about precisely how many samples we need to find some like epsilon optimal policy. So today we will like go to talk about our first statistical guarantees, like first guarantees for statistical reinforcement learning. Okay. So theorem 1, we say there exists an absolute constant C if we choose this sample size n, where n is the number of samples we need to query simulator for each SAH pair, we choose this n to be greater or equal to C times h to the power 4th and some iota over epsilon square, where iota will essentially, throughout this course, we will use iota to just essentially mean some log factor. Iota is equal to the log HSA over P. Okay. Then, with probability at least 1 minus P, the output pi hat of Vi will be epsilon optimal. Okay. So you can think this theorem actually not only says like when n go to infinity, this is accurate. We actually give a precise bound. We essentially says when n is greater than some absolute constant times this amount, then we are guaranteed this output of the value iteration algorithm is actually epsilon optimal. And just recall that by definition of epsilon optimal, last time we say we defined this in terms of a V star 1s1 minus V pi hat 1s1. This is less than epsilon. That is the pi hat policy. When we evaluate the value at the first step and the initial state is very, very close to the optimal value.
Separate iota. Isn't the whole top just like a constant?
What? Why is constant?
Or not
Oh.
constant,
Yeah, you can just put it there. But I think we in this course we will always like separate iota outside because a lot of times log term can be complicated. But for this course, I think usually we don't really care about log factor. So you can just think this is like some small multiplicative factor. Or sometimes like when you write some O tilde, you can just get rid of this.
But like the result is that it's like n has to be proportionate to like 1 over epsilon squared.
Yes, yes. Yes.
Where does the epsilon came from?
Okay, the question is where the epsilon came from. Epsilon is in the guarantee. That is, if we want to guarantee the epsilon optimal policy, we need to choose sample size that is scale with 1 over epsilon squared. That is, if we want to be more accurate, then we need more samples.
So epsilon is set by us, right? Set by
Yeah, it can be set by us. Yes. Yes.
I had epsilon optimal only for one state S1 or for all state S1?
I think for this course, we will just, like we said, for simplicity, we always make S1 to be like the fixed initial states. So we always assume we have any fixed initial states. But if you say your initial states is sampled from some distribution, you can also say this is an expectation of S1 sampled from some distribution. Like this is true. You can also guarantee the same thing with the same number of samples. Yeah. P is the probability. With probability 1 minus P. Yeah. Okay. Yeah. Okay, so we will first make some comments about theorem 1, and then we will spend essentially a lot of time in this lecture to prove the theorem. So first, we will talk about what is the sample complexity this theorem gives us. Sample complexity, as we discussed last time, is essentially we will define it as how many times we need to query the simulator in total to find this epsilon optimal policy. So in this case, sample complexity is we have n samples for each state action H pair. Okay, so that means we need n samples times the number of states, times the number of action, times the number of steps. So this is the total amount of samples we need to get the epsilon accurate policy. And we can essentially just multiply them together, and it becomes something like O tilde. O tilde, as we said, essentially we will hide some constant factor and logarithmic factor, and it will become some h to the 5th SA over epsilon squared. So this is essentially we're claiming that the value iteration will use some polynomial for the horizon and linear in states, linear in action, and over epsilon square samples to learn the optimal policy, to learn the epsilon optimal policy. One very important thing I want to claim is let's just remember in P is a transition. And if you remember like what is number of parameter or number of degree of freedom in this transition, the transition essentially depends on the next states and the previous states and the action. So essentially you can think this P is a matrix or any pH. pH is a matrix that is in S by SA. So the transition actually has S squared A parameters. So the transition at each step has S squared A parameters, and if you have H transition, has a time you kind of multiply the entire thing by H. But let's ignore the H dependence here. The important thing is, although the transition actually has S squared A dependence, we actually don't need to pay S squared A in the sample complexity. Okay. It turns out the entire samples we need to learn the MDP or learn the accurate policy is only depends on linear in S. So we'll actually talk about the this fact later. So it turns out the intuitive answer is like we don't need to learn this transition pH point-wise accurately. Okay, we will talk about like in what sense is this point-wise and that kind of thing later. Okay, this is the first comment. The second comment is we actually see the sample complexity scales with 1 over epsilon squared. This is another important kind of dependency we need to know, like how it depends on the epsilon. So this is like in terms of number of samples scale with 1 over epsilon. So let's just pretend like this is the entire sample complexity. If we make this equal to n, this essentially says the arrow epsilon is going to scale with 1 over square root of n. Okay. And we see this is like a typical error rate we see from concentration. Typical statistical error. So no matter in Hopton or in Princeton, the leading order term in terms of error is always like decreases 1 over square root of n. So this is essentially where it comes from. And so in the first comment, we talk about this SA dependence. The second comment talk about the epsilon dependence. So finally, I want to also comment a bit about the H dependence. So it turns out, so in this class, we will just introduce a slightly simpler proof. We will essentially get the h to the 5th sample complexity. But this h to the 5th can actually be improved to h to the 4th by using slightly tighter analysis. So we will actually introduce the coarse analysis as what we like in this class to make it simple, and we will kind of leave this analysis in the homework too. And we will kind of talk about what is the key steps to achieve in this tighter analysis. And later, we will actually also has lower bound to say, like this is essentially information theoretical optimal. So you cannot improve like to h cube or something. Like this h force is already sharp. Like there's no way to get better than h to the 4th by any algorithm. There's just no way to, like no matter what algorithm you use, you cannot get better than h to the 4th. This is information theoretical law. And you might think this h to the 4th is kind of like to some higher polynomial, and you don't know like why we have h to the 4th there. But it turns out I think some of the h is actually because of our characterization of epsilon. Because you can imagine in our MDP, we can like essentially assume the reward at every step is only from 0 to 1. That means the value itself is from 0 to h. So the value itself has a h scaling in it. So you can think epsilon is also something should be in 0 to h. So in that sense, although you have h to the 4th, but essentially 2 of the h has the same scaling as epsilon. So you can think epsilon kind of like cancels with some H scaling. So some intrinsic H dependency here is just H squared. So essentially, you can decompose this into H squared times H squared, and this is intrinsic. This is the essentially scaling cancels with so what I mean cancels with epsilon is instead of assuming this epsilon, you can assume this epsilon h, then you just get rid of h squared. This is just because some scaling we choose. Okay, any questions about the theorem? So I think this is our first theorem talking about some sample complexity. So it's kind of have a lot of statistical flavor. And we go to talk about what is exactly sample complexity, and we talk about how why each dependency makes sense. Okay, if no questions, we'll go to prove the theorem 1. So in order to, theorem 1 is actually not very hard to prove. So I first introduced the first lemma. We only needed 2 lemmas. Actually, one of them, you already did it in the homework 1. So the first lemma, I think the first lemma is essentially we want to guarantee the value has an epsilon error. But all we have is we have some estimated in the transition. So the first lemma, essentially, we want to relate the difference in terms of value to the difference in terms of transition. And so later, we can essentially bound the difference in terms of transition by concentration, and we kind of get the result down. So lemma 1 is about a relation of value difference and the transition difference. So the lemma states as follows, that for any policy pi, and any state horizon pair in S and H, we have the following inequality. We have following equation holds. That is the V pi S minus V hat pi H S equal to expectation. We'll talk about what's this notation later. M hat pi and the summation of the difference I from H to capital H, pi minus pi hat vi plus 1 pi si ai conditional sh equal to s. Okay, so we have the following holds for any H and S. Oh, we already said this for any H. Okay. So first, we introduce what is this notation of M hat. M hat, I don't remember if I say this in the last lecture, but M hat essentially is essentially you can think this is a new MDP where you use the P hat as your transition and R is your reward. This is the M hat. So taking expectation over M hat means essentially we're saying here, just remember the random thing here is the future trajectory. That is, we will have a AH, SH plus 1, AH plus 1, and till SH, AH. So all those things are random in this expression. So taking expectation by m hat and pi means A, all of the action A are sampled from pi. And all of the next states, sh plus 1 until s capital H is sampled from this p hat. So those are sampled according to pi hat, p hat, and pi. Okay, so this is the lemma 1. Although the formula is a little bit complicated, but essentially we will see very soon that is essentially if you just expand the value by Bellman equation and you immediately see like why this thing comes in, it's just by calculation. And we note this is the value in difference, difference in value. And this is a difference in transition. So we kind of like achieve our goal where essentially we want to establish the relation between the value difference and the transition difference. And we can essentially use this as our bound, say if the transition has no error or this error is very small and you can expect it. So this value is small just by looking at this formula. So we'll prove the lemma 1. Any question about the first lemma? You may also wonder why this is like asymmetric, like we have m hat here and instead of m. So actually you can also make it, this is like can be swapped. You can also make m here, but instead of v here, you will have a v hat here. So in some sense, this is symmetric. You need to have hat here and non-hat here, or you have no hat here, but hat here. Essentially, hat need to appear to one of the place. So we'll talk about the proof of lemma 1. As we said, the proof is essentially just follow the Bellman equation. So by Bellman's equation, we have following. That is, we look at the Q hat, QH, SA, subtract by Q hat, pi H, SA. And this is equal to pH, VH plus 1 pi SA, subtracted by P hat H, V hat H plus 1 pi SA. I think I should also say this V hat notation is defined as the value of this MDP. So essentially, we have this like modified MDP, and the value of pi on this modified MDP is denoted as V hat. So this Q hat is also denoted as the value of policy pi on this like modified version of MDP. So both just by Bellman equation. The first is by original MDP, so we expanded by PV. And the second is the modified MDP, so we have a P hat, V hat. This is very standard. And then we just add a term and subtract a term. So we essentially have PV subtract P hat, V hat. And we will add a P hat V, subtract P hat V and plus P hat V back. So this is equal to P subtracted by P hat times VH plus 1 pi SA plus P hat H times VH plus 1 pi subtracted by VH plus 1 pi hat. Okay. So all we are doing is we subtract this term, subtract the P hat V, and we add it back, add the P hat V back. So we didn't change anything, we just subtract and add back the same term. So this essentially gives us some structure. We know this the difference in the Q value can be decomposed as some difference in the P in the transition times the value of the true MDP, and plus essentially the value difference of the next step if after we apply the transition of the modified MDP. So you can see this is why we have that kind of formula there. So all we need to do is just we do one more step. That is, this is like a Q value. So we can, by Bellman equation, we can also do V value. Subtract by V value of this H. So in terms of V value, all we need to do is we just take in the action, taking over expectation over this policy pi. So we just write it as expectation, taking expectation over action through policy pi, and the pH subtract by pH hat, VH plus 1 pi, SHAH, condition on SH equal to S. This is the first term. And we can further write the second term. It turns out the second term is precisely, we can take expectation over M hat and pi. So pi is something we need to take expectation because we do the V value, and we can essentially absorb this transition P hat into taking samples according to P hat. So sample according to this modified MDP, and we look at the value difference at the next step. Okay.
Wait, can you explain how you got this?
About second term again.
Just the V.
This one? What? This one? Or I think we can also just quickly write this out, right? By notation of this notation, we know this is equal to taking expectation over S prime sampled from P hat dot SA, and this is S prime, right? So we're essentially just write this thing as an M hat, and then we take another pi over the action. So this is all we need, all we did. We didn't do anything else. I think the important thing is to observe this is precisely corresponding to, we take a next step according to this modified MDP. So that's why we can write it in this compact form. So we didn't do anything complicated, and it's just we're writing some compact notation so that we can see things through a recursive fashion. So we can think this is essentially we kind of relates the value difference in each step to this is like the transition difference in each step and the value difference in the next step, in H plus 1 step. So we can essentially expand the recursion. Expand the recursion means for the value in the next step, we can again apply the same argument, and we can decompose into the transition difference in the next step, h+1 step, and the value difference in h+2 step. And we can go on, and eventually we prove this lemma. Any questions so far about this proof? Yes, please.
In the recursion, the first term has expectation with respect to pi, but then at the end that summation has expectation with respect to m hat and pi, so it comes to the m hat again.
Sorry, could you say the question again? Second part of your question.
Oh, just that the final expression has expectation with respect to m hat and pi.
Right.
But it seems like the first term.
First term it only has pi, but I think this is this is only h, and this is h+1. And when you expand this again, like vh+1, that will again equal to the first term has this, but you have m hat outside. So this is where like you can think this vh+1 again will be equal to ph+1 minus ph+1 hat, and then value difference in the h+2 step, where the ph+1 minus ph+1 hat now is inside this expectation. So that's why you have a m hat here. Okay, I would just do a bit more then. What I'm saying is you will have let's say in the high level, you will have like delta V. This is like a value difference in the first step is equal to expectation of pi. Let's call it delta P. Delta P is essentially a lot of things there. And plus e pi m hat, and delta V in 2. So delta V in 2, we will also have expectation of pi of delta P2, and plus expectation of pi m hat, and delta V3. So what I'm saying is you kind of like plug it inside here, then the P2 term will actually not only have this expectation in pi that is taking expectation of A2, but you also have this expectation of E pi and M hat that is taking expectation of the first, the second state and the first action. So eventually when you kind of like expand this outside, eventually you will have like delta V1 is equal to some summation of E M hat pi and delta PH. H from 1 to capital H, where this expectation is actually like a concatenation of a lot of expectation of like state action at different steps.
What happens to P1?
P1 actually doesn't have m hat, you're right. But P1 essentially has no next states, so you don't. Yeah, P1 is like first step, so you don't have m hat there. Okay. So we will talk about the second lemma. So the first lemma is pretty straightforward, it's just directly by Bellman-Optimal equation. Essentially, we decompose the value difference by the transition difference. You can expect, of course, like if transitions are very close, then two values should be very close. Essentially, we just have the mathematical formula do that kind of decomposition. And the second step, essentially, now we can say we can bound the value difference by transition difference. The second step, essentially, we use concentration to say how much value can be different. Okay. So we'll do lemma 2. Lemma 2 is essentially what we have already proved in homework 1. So for fixed SAH and fixed value function V, let's suppose in 0 to the h to the power of s. That is a s-dimensional vector with value taken from 0 to h. We say with probability greater or equal to 1 minus p over HSA, we have that let's say we have that this ph subtract by p hat h, where p hat h is our estimate in value iteration algorithm, times this value at SA is less or equal to C times H iota of n, where this iota is equal to log HSA over P. So this is actually precisely the very last question of the homework 1. With slightly rescaling, where in the homework 1, we kind of say the value is in minus 1, 1 to h to s. Here we say 0h to the s, so we kind of have additional h factor here just because of scaling. And also, I think there we don't precisely get this like this probability. You can just say 1 minus delta, but you can easily replace this by like this entire quantity as delta. And we choose this specific p over HSA because later we want to do the union bound. But in the homework, essentially, you prove this with probability 1 minus delta, and you can do everything with the C1 and the log 1 over delta over n. Okay. And I don't know how many of you have done the homework, but essentially this is done by applying Hofstad's concentration inequality. Which is a very good exercise after we learn all the concentration inequality. Okay, so I Any questions? I guess the proof will be left as a homework, already said in homework 1. And I think I want to emphasize something a bit more. Like I think in the earlier phase, we talk about the sample complexity, where we think one very non-trivial fact of this like tabular MDP is we don't actually require the S squared A number of samples to learn the transition. We actually only require SA. So I think the key thing here is we actually only do this for fixed value function, or we can extend this. This can be extended to random value function. But the randomness need to be independent. Of p hat. Okay. So we need to know what is the probability statement here. So this is a probability statement that is with probability of 1 minus p over SHA. So the only thing random in this quantity, like this is a fixed value function and this is an original transition. There's no randomness here. The only thing random here is the p hat, where the samples we collect, remember this p hat, we use empirical frequency to estimate this transition. So the sample we collected, S1, so this is with probability over the sample we collected, S1 prime, till Sm prime. So those samples will essentially form the p hat. Okay, so those things are only random thing. And we're saying we actually, this does not only works for fixed value function, but also works for from random value function, as long as this randomness is independent of p hat or independent of this S1 to Sm prime. So the reason like we can handle this independent thing is in that case we can first just draw this random function and then apply this lemma 2, because after we draw the random function first, and because this p hat is like completely independent of this random value function, so we can still basically apply the same thing and we get the same result. And later here, it's actually very important, we will use this fact. I also want to make some comments that lemma 2 essentially says as long as n equal to some theta poly h or theta tilde poly h. Let's say h is just some scaling, so let's not care about h. So we already have concentration. At all state action pair, or at SA. So that means the total number of samples is like, again, n times HSA, which will be scaling as SA instead of S squared A. So this lemma 2 essentially already kind of contain the most important fact. We say we don't require S squared A number of samples to learn a value function well. We actually only require SA to learn a function value well, because for each SA pair, we actually doesn't need to pay anything in terms of S. Okay. We just pay, as long as this n equal to some poly h, we can push this arrow to be something very, very small, and we kind of already in some very good shape. I just want to say this in general, very important thing is we actually consider this as a fixed value function. and or like an independent value function. So I just want to say, in general, if this is not fixed value function, if this is like some adversarial value function, this is not true. Okay, so we don't have these sharp guarantees. So in P set 1, we also kind of have another result. We will ask you to prove this. P hat minus P is a infinite norm or TV norm, like TV distance is less or equal to O tilde square root S over N. This has like some logarithmic term. So this is what we traditionally, in a sense, we require, like if we really require some TV distance, like probability to learn accurately, we typically like measure in terms of total variance distance. In this way, we actually require N to be something linear in S. This is also equivalent to saying we need the max S P hat P, and this V value this is less than O tilde square root S over N. Well, here we only essentially has, this is like O tilde 1 over square root of N. Okay. If ignoring the H dependency here. So you can see if we use this type of guarantees, then this will actually lose by a factor of S, because for every state action, we already need to pay some number of S samples to push this arrow to be something very small. In that case, we will pay S square A samples. So the major difference between here and there is this is like for fixed value or for random value independent of this P hat. Well, this can be for adversarial value. This is essentially because we're taking max over P of the value, so this is adversarial. For P hat. That is, we can first draw some randomness P hat, and then we can essentially pick some V that is like the worst case against the P hat. So of course, this is like very loose. So the key observation here is for reinforcement learning. If our task is just want to learn some epsilon optimal policy, that is not necessary to learn P to be accurate enough for all V. Okay, so this is not necessary, which IE is in like in TV distance or something. We only need to make P minus P hat to be accurate, concentrate for certain V's with good property. good property in terms of either it's fixed or it's like random, which saves S sample complexity. S factor. Sample complexity. So the key takeaway is essentially, in short, for reinforcement learning, all we care is the policy to be great. So in that case, it turns out we don't actually need to learn the transition very accurately in terms of, in this sense. Like we don't need to learn transition so accurate so that it works. For any V, this is accurate. We only need for some specific type of V, like either fixed or not, like random, as long as this expectation is accurate, and then we're good. So that's why we kind of like bypass the number of parameters in the reinforcement learning. We don't pay S square A, we only pay SA. Okay, so we will see this in the final proof for the theorem very soon. Okay, any questions about this part of discussion? Okay. If no questions, we will just directly to prove the theorem 1. We will immediately see like where it comes in mathematically about this key observation. Okay. So now we're at the final step. So final step, we will actually look at what do we want to bound. The thing we want to bound is, we say the suboptimality of pi hat, which by definition, we need to look at this V1 of pi star as 1, subtract V1 of pi hat as 1. Okay. And remember in the like we want to bridge this to, we want to like link this to the transition difference so that we can use the concentration. However, just remember our lemma 1, we actually use something different. We actually calculate the value difference in terms of the same policy but different MDP. So we're doing V minus V hat, but we need the same policy. So here we essentially use that lemma by just add a term and subtract a term, where we do V1 pi star S1, subtract by V1 hat pi star S1, and plus V1 hat pi star S1, subtract by V1 hat pi hat S1, and plus V1 hat pi hat S1, subtract by V1 pi hat S1. So we subtract term and add it back, and subtract a term and add it back. Okay. So this is like precisely equal. And now we have 3 terms, essentially. We will group the first 2 together as a term A, and group the last 2 terms together as term B. And for this term, we know this is always smaller than 0 because pi hat is actually optimal for m hat. Just remember how we computed this pi hat in this value iteration algorithm. We directly do the Bellman optimality equation on this m hat, on this like modified MDP. So that's why on this modified MDP, pi hat is actually the optimal policy because it satisfies the Bellman optimality equation there. While pi star, although it's the optimal policy of the original MDP, is suboptimal in this m hat. So that's why this value is actually greater than this value, so this is smaller or equal to 0. So in order to upper bound this value difference, all we need to upper bound is the term A and term B, which is precisely goes back to the lemma 1 case, where we look at the value on different MDP, on different transition, but on same policy. Okay. So now let's bound the term 1 and term A and term B. Term A. This is equal to directly by lemma 1 m hat pi and summation h from 1 to capital H with this p subtract p hat vh plus 1 star SIAI condition on S1. Okay. So this is just directly by lemma 1. But the most important thing we observe here is if we want to use the lemma 2, we actually need to argue about whether V being fixed or V being like an independent random thing. But this is the optimal value function of the true MDP, where true MDP is not anything random. True MDP, there exists some underlying P and R, so it's not random at all. So this is actually a fixed value. So in the sense, it doesn't depend on S1 prime, S2 prime to Sn prime at all. So where we can safely apply the lemma 2. We will actually say by lemma 2 with probability 1 minus p, because lemma 2 essentially say for each state action, this event holds with a probability 1 minus p over HSA. And then we can just use a union bound. So we say for 1 minus p probability, this thing actually holds simultaneously for all SAH pair. Essentially, the last time we talked about the union bound. So we can just apply the same concentration for all state action. The union bound will apply lemma 2 to all SAH simultaneously. Okay, so we say this is smaller than C, just times So each term, if we push expectation inside, each term is smaller than C times H and iota over N. But we have an additional summation there, so we just say summation H from 1 to capital H. And this is equal to C times H squared and iota over N. And eventually, just remember in our, in the theorem 1, we actually choose n to be greater or equal to C prime for some large constant C times h to the 4th iota over epsilon squared. So essentially, we will use iota to cancel iota and h to the 4th to cancel h squared here. And we choose constant large enough so that it absorbs anything constant here. And then we say this is less or equal to epsilon over 2. Okay. We choose constant large enough so that it absorbs this constant, but also has an additional factor of 2 here.
Professor?
Yes.
Where does the small h used?
Small h used?
Yeah.
Where
it is used, the small h?
So essentially, in this concentration, we actually, although this is apply for the transition difference for small h, and because we have n samples, so the upper bound actually doesn't depend on h. although the transition difference is like at H step, but the upper bound doesn't depend on H. So what we are doing is we push the summation outside, and for each step we apply the lemma 2, and so it's this bound. The upper bound actually doesn't depend on small h. So that's why when you do the summation, you just simply have a multiple factor of h. Okay, so this is one term. We essentially just need to argue the similar thing for the second term, and then we're done. Second term is slightly more complicated to argue, but we can manage that. So we look at the B term. Again, by lemma 2 or lemma 1, we do the decomposition that is equal to expectation over m hat and pi. We again have this summation, h from 1 to capital H, ph, subtract by ph hat, vh plus 1 pi hat. SAI, conditional SY. This case is definitely trickier because this value here, in the first argument, we just argue this value v star is like fixed. But here, this is clearly random. Okay. This depends on pi hat, where pi hat actually depends on the sample of simulator. So this is random. But the key observation here is we note this value, vh plus 1 pi hat, only depends on since this is value at h plus 1 step, so it only depends on the policy at later stage. Okay, vh plus 1 pi hat, till v capital H pi hat. It actually doesn't depend on the policy in the earlier step. So we doesn't really care about what are the policy on the earlier step. We can already fully determine what are those values. And the next thing is we observe the value iteration is a dynamic programming from back to the front. So we actually calculate this pi hat h, only use the data that happens like after h. So that means those policy, the computation of those policy only depends on the randomness in this pi hat h, only depends on the randomness in this p hat h. Okay. Only depends on the randomness in the very last step. While the pi hat h plus 1, h minus 1, depends on the randomness in the last two steps. And until the very first policy, this pi hat h plus 1 depends on the randomness in all the steps after h plus 1. The important thing is it only depends on data in the later steps, the next states in the later steps. It doesn't depend on the next states in the previous step. So this actually creates an independency here. Because remember in this value iteration, we actually, for each state action and for each SAH pair, we actually draw samples independently. So that means this randomness in this pH is actually independent to all of the later transition randomness. Okay, so this is actually the very key step. That observe this value only depends on the transition in the later steps, which is actually independent of the transition samples in the later step, which is actually independent of the samples you observe at each step. So finally, we just apply the same argument again. So this is less or equal to some c times h squared iota over n. And whereby choosing n large enough, we can say this is also less or equal to epsilon over 2. And this essentially finished the proof. Because a is less than epsilon over 2, b is less than epsilon 2, and the middle term is less than 0, so that everything, like the suboptimality, is less than epsilon, less or equal to epsilon, and we're done. Yes?
What is the factor above n in the square root?
Oh, the question is, what is the factor above the n? This is the iota, the logarithmic term. Just whatever the logarithm term here. This is like in the theorem. Remember in the theorem 1, we talk about the sample complexity, right? In the theorem 1, we say we need to choose n large enough, larger than some threshold. Where in the theorem 1, the threshold is exactly some absolute constants times h to the 4th iota over epsilon squared. So this is just saying by our choice of a number of samples. And then we can use this h4, cancel this h squared, and iota cancel iota. And epsilon, we put it here. And all we need to do is make this constant large enough so that it's equal to something like 4c squared. Yes?
Could you explain again why P of h plus 1 is independent of P of h, even though we assume, I think with the Markov property, that the transition...
Yeah, I think, so I think the way we've written this is a little bit inaccurate. And so we just think of, just consider what do we mean by this independent thing. Just recall that, so the samples we collected for this p hat is we have S, A, H, and we collect a bunch of next states, right? S1 prime till Sn prime. And then for the next step, S, A, H plus 1, we also collect a bunch of next samples.
Oh, okay, so it's not
yeah.
within the same trajectory.
Yeah, they're not on the same trajectory. They're just completely different. Yeah. Completely independent. So value iteration is actually a very simple algorithm. We will actually study a lot throughout the course on different settings because it's basically just biodynamic programming. But here in this simulator setting, I also want to introduce one additional algorithm so that which is also very frequently used in the field that is called Q-learning. Let's just first recap how do we do the value iteration. Value iteration essentially follows the Bellman optimality equation that we do the Q hat SA is equal to R HSA and plus P hat V hat. Essentially, this is the key update equation. And where we know this p hat is used we use the empirical frequency to estimate this transition probability. Where this p hat s prime given conditional SA is equal to summation I from 1 to n indicator of Si prime equal to S prime over n. We essentially will use n data, we collect all the data. Then we update. This is kind of like the batch update. In practice, there's another type of algorithm where we don't do the batch update. We actually do some incremental update. We do online update. And that is, we don't like wait till we collect all the data and we do this update. But we, as soon as we observe like a single data, we will do some update. That is essentially the Q-learning algorithm. So we will do online updates. Which we will only use the most recent data. But of course, in the statistical setting, like when we draw some random samples, if we just use the most recent data, then inevitably there are a lot of noise in it. So because data is very noisy, so that means we should not just use only the recent data, but we somehow should use some previous data to average the noise out. So what we actually will do is some incremental update. So that is, we will do some updates based on the previous value we get. So it turns out the updated equation is something like this. QHTSA is equal to 1 minus alpha. 1 minus alpha fraction of QT minus 1 HSA. That is, we have some previous Q value, and we do the 1 minus alpha fraction. We kind of like trust the previous Q value. Well, with alpha t fraction, we trust the new data. And where new data is single data, we look at the reward and the value at the next step. So you can think this is essentially some learning rates. And this is the t sample. From simulator. So I think I will stop here. In the next lecture, we will continue talking about this Q-learning and like benefits, advantage and disadvantage compared to the value iteration. And we probably won't go into that detailed proof in terms of the sample complexity of Q-learning, but we will give the results and talk about qualitatively, like what's the difference, what's the similarity. And then we will move on to the exploration scenario, the online scenario, more challenging than the simulator. Okay. Thank you.